we have now reached the final module of this course, which focuses on responsible AI. In Lesson 1, we will introduce fairness and bias mitigation in ML. Today, we will introduce fairness and responsible AI. This will begin with defining responsible AI and the dimensions that compose it. We will define fairness, both at an individual and group level. Then, we will discuss fairness throughout the ML lifecycle, from ML problem formulation, data collection and processing, model training and tuning, testing and evaluation, to deployment and maintenance. We'll begin with an introduction to fairness and responsible AI. Responsible artificial intelligence development includes creating tools that respect fairness, security measures, and privacy measures. Responsible AI also considers explainability, robustness, and transparency of AI systems. Quoted from the Organization for Economic Cooperation and Development in May 2019, AI that is innovative and trustworthy, and that respects human rights and democratic values. Why is responsible AI important? It is the right thing to do. Additionally, it helps prevent unintended impacts, allows auditing of AI systems to gain trust from users, and can help meet regulatory and policy requirements. Which dimensions, or pillars, principles, virtues, should be part of responsible AI is debated globally. However, AI designers, developers, and operators should aspire to certain core virtues. See the slide. The importance of a virtue varies depending on the use case. Other key attributes of a service include overall accuracy, cost, feature set, and latency. But these attributes are already considered in the normal process of building a service. Keep in mind that different organizations might capture these dimensions differently. For example, the Organization for Economic Cooperation and Development, OECD, lists 5 AI principles, https://www.oecd.org/going-digital/I/principles. Questions to ask about each dimension: fairness and bias. How does the system impact different subpopulations of users? Privacy and security. Is data protected from theft and exposure? Robustness. What is the mechanism to ensure that the AI system operates reliably? Explainability. What are the mechanisms to understand and evaluate the outputs of the AI system? Governance. Is there a process to define, implement, and enforce responsible AI practices within the organization? Transparency. How is information about the AI system communicated so that stakeholders can make informed choices about use of the system? The dimensions might also be known as pillars, principles, virtues. The focus of this lesson is fairness as one of the 6 dimensions of responsible AI. With fairness, you need to consider how a system impacts different subpopulations of users. Subpopulations might be defined by characteristics such as ethnicity, sex, primary language, physical capability, or religion. Make sure that the system itself does not perform too differently on different subpopulations. To be responsible ML practitioners, you need an agreed-upon technical definition for fairness. Most generally, this would be fairness as the absence of bias, where bias, in the responsible ML space, means some sort of disparity in performance. Generally, we strive for equity. Everyone gets what they deserve, regardless of group membership, or equality. Everyone gets the same. Equality can be impossible to achieve in practice with limited resources. For example, a bank cannot give out infinite loans. Bias is an overloaded term in the ML community. Depending on the domain, different practitioners have different meanings for bias. For example, sometimes bias refers to a specific component in an equation. Sometimes, bias is used to talk about disparity in system behavior. Let's look at a hypothetical credit lending scenario. A user requests a credit line increase. Because of a large request volume, the bank uses an AI system to initiate a credit lending model. The system indicates a low credit score as output for the requester. A score of 0.3 results in a denied outcome. Therefore, the user request is denied. In addition to scaling requirements, an argument can also be made that an ML system may help reduce certain types of bias compared to manual evaluation processes. Keep this workflow in mind as an example of how a user experiences an ML model outcome. This is also a classification example because the outcomes are yes or no, approved or denied. When building an AI system, it is important to consider whether the system should be fair with respect to individuals or with respect to groups. Making a model fair for groups means that the outputs will be similar when aggregated on the group level. However, group fairness does not consider individual merits and might result in choosing the less qualified members of a group. Individual fairness requires that two similar individuals, regardless of which group they belong to, are treated/impacted similarly. This is difficult to achieve in practice, which is why group fairness is more commonly used. A model that produces the distribution that is shown in this chart would be considered fair for the two respective groups, married and single. However, individuals can exhibit multiple demographic attributes at the same time. If these multiple attributes intersect, new, more granular, subgroups emerge. It's important to understand if the newly defined subgroups still receive fair outcomes. A possible intersection of attributes is given by marital status and an additional group status. In the chart, columns refer to group status and rows refer to marital status. Certain subsets have favorable numbers of outcomes. Overall, both marital status groups have the same number of positive outcomes, 7, but they are concentrated for a certain group attribute. If you now overlay a second demographic variable, in this case, homeowner or renter, observe that the positive outcomes are disproportionately concentrated in different subpopulations. This example shows that different subgroups might experience additional disparity. As indicated in the chart, the married renters group has 0 positive outcomes and 6 negative outcomes. This is a hypothetical example, and you could think about many more attributes. In fact, those attributes don't need to be binary. The reason that they are binary in this example is that most of the literature and research actually distinguishes on binary attributes. One idea at this point would be to build separate models for each subgroup. However, in the United States, building separate models for different groups or different attribute groups would be against the law. Now that we know about responsible AI and fairness, we will illustrate fairness throughout the ML lifecycle. Consider a typical ML lifecycle from ideation to creating predictions, answers. Where in this lifecycle should you consider fairness? Fairness should be considered in all stages of the ML lifecycle. In the next slides, you will learn about a few practical examples of how to consider fairness by using techniques to mitigate bias. Everyone needs to understand the business problem. By understanding the use case and problem, you can prevent harm. Try to classify the risk that is associated with a particular use case, and take efforts to scrutinize potential misuse or harm that could be caused by building this ML solution. Ask questions such as, what is the use case? What are possible risks? To ensure that you consider different perspectives, discuss your modeling approach with different stakeholders and diverse groups. Examples of diverse groups include the following: fairness experts, privacy experts. Legal examples of diverse identities include the following: gender, sexual orientation, race, nationality, religion. If bias exists in training data, the model may produce biased predictions. This is similar to the infamous garbage in, garbage out principle. You should assume that models are inherently biased and try to find the bias rather than assuming that there won't be any issues. A proxy is a variable that secretly encodes a sensitive attribute. For example, zip code could be a proxy for ethnicity, same with income, which could be a proxy for ethnicity too. You should question, is the training data representative of different groups? Are there biases in labels or features? Does the data need to be modified to mitigate bias? If you identify bias in the data, you can take certain steps to remove the bias. For example, you could try to remove the problematic features or transform the dataset. However, removing the bias isn't as easy as you might think. As an example, assume that you were to remove ethnicity features but keep zip code. Zip code tends to be a proxy for ethnicity, so the information remains encoded in the dataset. Keep in mind that, in some domains, there is a legal obligation to delete sensitive attributes. In such cases, there's no choice. One way to transform the dataset is relabeling. Find a data point in the favored group that is similar to a given data point in the unfavored group, and assign the outcome of the favored group to the disfavored individual. These are not the only techniques. There is also reweighting, learning fair representations, and other types of data transformations. Beware, sensitive attributes are often correlated to other attributes, so check for correlations before deleting attributes. Also, in some domains, sensitive attributes are useful, health, so you should not delete those. When selecting an algorithm, it is important to consider the needs of your stakeholders. Some algorithms are easily interpreted but might not have very high performance, while others perform really well but are hard to explain. At AWS, providing explanations for why a particular prediction is given is a top priority in these cases. Another consideration during algorithm selection is whether it is possible to modify the algorithm to train in a certain way, by adding additional constraints. Not every type of algorithm will be modifiable in that way. Many different bias mitigation techniques exist, and it is possible to use them at different stages. You can mitigate bias by constraining the way that the model learns, this includes tuning, or by modifying the results of the model. During the testing stage, it's important to keep testing how fair the model is. Different measures are available for this. One approach is to use general ML metrics but split them by group. Another important step could be to include confidence scores. A confidence score is an estimation of the confidence or certainty of any prediction. A confidence score is usually expressed in the form of a probability. It is important to reflect on if the model has been evaluated using relevant fairness metrics. After a model is trained, you cannot assume that the model will continue to perform well over long periods of time after training. This is mostly because data distributions evolve over time. Therefore, consider monitoring for model drift and make sure that the model is used in a location that it was built and trained for. After a model is deployed, it will generate predictions for end users. End users don't usually have visibility of the inner workings of a model, so it is important to offer them ways to inquire about the decisions that they receive. This will help end users understand and challenge the model if necessary. The next lesson will explore building fair models, exploring data, and bias metrics. Thank you for listening.